Bismillahirrahmanirrahim. Welcome to Easy Learn, and as you know, this is the episode 3. And first of all, let's recap the episode 2. What we had already discussed in the previous episode, and we had already discussed in the previous episode bipolar junction basic structure, epitaxial planar diagram. What is the epitaxial layer, and substrate, emitter base junction, emitter base and collector differentiation with the help of the circuit symbols and NPN PNP physical representations as well. And today's topic is we will try to discuss the basic BJT operation. In order to operate the bipolar junction transistor properly as an amplifier, two PN junctions must be connected properly, because we had already discussed. Just trying to recap. In the normal PN junction diode, this is the P, and it can be connected as a forward bias or just as a reverse bias. There are two cases, forward or reverse bias. But when we have three regions, PNP or NPN, means to say three different types of regions, then there is maybe something change. There we have the possibilities are increased, because we had two depletion region. Here we had because this is, we are know that how we can calculate the possibilities, number of possible cases. The formula can for this is 2 raised to power here 1 is equals to 2. They basically, the formula is 2 raised to power n. N is the number of the depletion regions, and if here the 2 raised to power n means to say that you have to calculate the number of depletion regions. Here in the normal PN junction diode, it has only one depletion region, because there is just two P type, one P type and one N type. So 2 raised to power 1, two possible cases. Either it can be operated in forward or in reverse bias. But when there are two depletion region, 2 raised to power 2 is equals to 4, means to say we have two possible cases, 4 possible cases, sorry. And these are the cases. For example, cases are these, that first depletion region, that is the emitter base depletion region, and the second one is the base collector or collector base depletion region. First case is, for example, both are forward bias. Second is both are reverse bias. Both can be in reverse bias state. If we can also operate forward bias and reverse bias, and this is reverse bias, this is forward bias. But I will not explain the other cases one by one. We will discuss all the cases later on when we will grow in this episode. We will learn further things so here we will just discuss this case when the emitter base junction is forward bias and collector base junction is reverse bias. This case, because our today's topic is this case, and this is very important case, and the very used very many of the applications are based on this case. So important case will be discussed here first. And when our emitter base junction is forward bias and collector base junction is reverse biased, then this can be used as, by BJT can be used as operated as an amplifier. This can be called as BJT is operating as an amplifier. In order to operate the BJT properly as an amplifier, the two PN junctions must be connected properly. Emitter base junction and collector base junction must be correctly biased, and I will use NPN today. Here I will use NPN. PNP is same, and NPN most commonly used, so I will use NPN. Same PNP case. This is the N this is N, P, N. Okay, and P and P is same, everything in the P and P is same except the role of electrons and holes. Voltage polarities are reversed, current directions are also reversed, everything except is same. So this P means is the positive side, and positive side here we need a limiting resistance, and positive side is connected with the battery, and this is the battery, positive terminal of the battery, and this is the negative terminal. Here this is the resistance, and after this resistance, limiting resistance once again, and this is connected with in order to set this base region. This is base, this is emitter, and this is the collector region. In order we want to operate our base emitter junction forward bias, we should be connect the base lead with the positive side of the battery, and negative should be connected with the emitter side, because when N is connected with here in the normal PN junction case, this is PN junction diode, when P is connected with positive side, N is connected with negative side. Remember, PN junction, this is the forward bias case when it allows to current to flow. P it comes from the P stands for positive, N stands for negative. Basically it is when operated in forward bias situation, when it allows the current to flow, this is the P is connected with positive, N is with negative. Remember always, P is connected with positive and N is connected with negative. Here N is connected with positive side, because this negative is going to again connect with this E, and we are here trying to also ground this to operate its circuit properly. Remember that this is a state. I will also explain here that there are three possibilities, common emitter, common base, and third one is the common collector. These are the three possible cases where we can use. Common emitter means that, for example, here you can see that this base region is used as an input. This is our input, okay, and we can control this input, and from this input we can control our output. This side is our output, but we will discuss these other things later on. Right now just focus on this circuit. This is positive. Here this you can see that this emitter is common. Here means to say this is also connected with this battery and this battery, here both sides, while this is not common. This collector is only used with this side, base is only. And if we use a common base, then we will use this base circuit from here and here, both sides. Means to say that, for example, this is a base, common base is used here like this. This is our now input, and this will be on output between base and collector. No, base is common. Same the way collector can also be common. When collector is common, this can be operated like that. Collector can be used with base. Okay, then this is a collector. This is our collector, because this collector can be connected with both sides. Collector can this is nothing. In case of the common collector can be common with base terminal and with the emitter terminal. Anyway, but common emitter is mostly used case in order to operate the bipolar junction transistor as an amplifier. This is a very important case. If we want to operate these connections must be properly biased, and you don't need to forget in order to take further understand, we will try to discuss the internal what happens inside this internal working principle of the bipolar junction transistor. Okay, let's take the internal inside look. This is a bipolar junction transistor. This is very important discussion starts for right now. Please note everything that I am explaining now. This is very important discussion. If you understand this, then I think that for the next coming up videos, you will also understand. This is the basic structure. This is the this is straight line. I'm sorry. This is your collector. This is collector. This is emitter, and this is narrow base region. Heavily doped emitter, moderately doped collector, and narrow base region. This is the metallic lead. Okay, this is the metallic leads. This is the metallic lead over here, and this is the metallic connections from here. Emitter, when emitter is connected with the negative, because we are discussing NPN, remember, we are discussing N, P and N, and this is emitter base, and this is the depletion region. These are the this is the depletion region of base emitter junction, BE, and this is the this narrow width I showed here. This is the depletion region between the base and collector region. Base collector depletion. This is the depletion region of the base collector junction, and these are the metallic leads. Same metallic leads. The heavily doped N-type emitter region has a very high density of the free electrons. Okay, you must remember this, that the emitter region, because this is an N region, so it means it has a very high density of conduction band free electron. Conduction band electrons are, for example, this is nucleus, and these are the electrons, and these are the outermost electrons are called valence electrons. These, let's say, these are the outermost electrons, and these are the called valence electrons. If we provide further energy to these electrons, there is another shell outside the valence electron, imaginary shell, you can also say. If the electron may go to this state, and this is called the conduction state, when it is available for the chemical bonding and other reactions as well. So at this state, that it is called, the electron is in excited state and gains the energy, and this is called the conduction band. So when it comes from here, negative potential, when it is connected with the negative source, these electrons are coming from the negative side, negative source. So negative, because this is connected with negative from both sides emitter, so negative repels, and here is a push of the electrons, because from the back side negative charge continuously pushing these electrons to move to upside. Too many electrons over here. For example, these are all electrons. Okay, and this is enriched with the conduction band electrons. Remember, once again I'm repeating, these are all conduction band electrons. This is a push of the electron here from this side. This is a forward bias. It will go when from depletion region, pass from the depletion region, it will lose a little bit energy, and but still it continues, because there is a forward bias. Depletion region doesn't affect too much, and here the electrons reaches. But here are some holes. This is a hole, this is a holes, this is are the holes, these are some holes available, because this is a base region and this is narrow base region. These are some holes, because some depletion region is really very narrow. so not too much holes, but as you know, p type has a maximum holes because it is positively charged and very less electrons. Moreover, it is also connected with positive side of the battery. Here this is a positive terminal and positive is continuously providing the holes. Here electron and hole pair definitely always trying to merge into each other, because positive and negative charge always attracts each other. But remember that once again, this is very important to explain here. This is very thin region and very few, these are the push of electrons. Think this, that the water is coming to this side, think that water is coming to the upside, and there is a very little pipe that is an outlet pipe. Then most of the water will try to go out from this pipe, but due to this very thin vessel or pipe here, very low path or a very thin path, most of the water will continue to pass. Very few electrons will go through this path from the base region. Most of the electrons cannot recombine with the holes. The few electrons will combine with the holes, lose energy, and they will go after combination into their conduction band, into their from conduction band to valence band. And further discussion will be continued from the next time.